Hello, hello. Am I audible? Hello, am I audible? Is my screen visible? Hello, hello. Okay, I think I'm audible and my screen is also visible. So let's start this live session. Hello everyone, I am Pankaj Kapdi and I am a NPTEL PMIF TA for the course of Engineering Mathematics 1, and this week we'll be discussing some problems related to the video lectures or course material for the week 9, and the problems will be mostly based on finding dimension or basis of vector spaces, some linear trans properties of linear transformation, and finding their rank and nullity. Okay, so let's start with the first problem. So this is our first problem. Here we are given three vectors, u, v, and w, and we have to find out which options are correct. And there are four options. So basically, we have to find if the set of these vectors u, v, and w is linearly independent or not. Okay, and what is their span? So what is the subspace generated by these vectors? Is the span of these three vectors same as the span of the two vectors, that is, or their span is not are not equal? Okay, so we'll see what happens in this case. So we have to find out if these vectors u, v, and w are linearly independent or not. Okay, so when these vectors are linearly independent. So these vectors being linearly independent means whenever a linear combination of these vectors, let's say c1u plus c2v plus c3w is 0, then the only solution of this equation is c1 is 0, c2 is 0, and c3 is 0. Okay, so we allow only this unique solution. Okay, you can see that this c1, c2, and c3 equal to 0. This is already a solution, but we want that this is the only possibility. There are no other solutions. Okay, so if that case happens, then we say that these vectors are linearly independent. Okay, so what we are getting in our case, if we have these vectors u, v, and w, this is c1 multiplied with 1, 2, 1. So this is our one vector, plus c2 multiplied with another vector, which is 3, 1, and 5, plus c3 multiplied by 3 minus 4, 7. Okay, and we are solving for the 0 vector. We want that this system of equation should have a unique solution, and which is the 0 vector. That is, we are essentially solving a system of linear equation where that system in the matrix form is given by. So these are entries of the matrix. The first column is the first vector, second column is the second vector, and the third column is the third vector. And we are solving for this system of equations in the matrix form c1s C1, C2, C3 are our variables, and we are solving the system of equation for the zero vector. Okay, and we want that this system should have a unique solution, and that solution is must be the zero vector. Okay, so if we show that the solution is a unique, there is a unique solution, that means this vector will be linearly independent. Okay, let's see if that system has a unique solution or not. Okay, so we will take this matrix and we will just reduce it to the row echelon form. Okay, so row echelon form means everything below the diagonal must be 0. So 1 2 1, 3 1 5, 3 minus 4 7. Okay, note that we have to make these entry 0 by using the elementary row operation. If by using elementary row operation we are able to make this 0, then that form will become a row echelon form, and from that we can calculate C1, C2 and C3. So let's see. So what we'll do, we apply some elementary row operation. Okay, we want to make this 0. So how can we make it 0? We'll multiply the first row by 2 and then subtract these two. Okay, so 1 3 3. So what we are doing, we are changing our second row to minus twice of row 1, right? Okay, I'll not write these, I'll just write the equivalent form. So you'll get here 0. Okay, you are multiplying by 2 in the first row and then you are subtracting that from the second row. That means this will become minus 5 and this will become minus 10. And then we have 1, 5 and 7. Okay, again we want to make this entry 0, and how do we make it? We subtract first row from the last row, and then we get 0 minus 5 minus 10. So 1 minus 1 0, 5 minus 3 is 2, and 7 minus 3 is 5. And that is equivalent to, what we'll do, no, this is 4. This is not 5, this is 4. Okay, multiply by divide by 5 in the second row, or minus 5. Okay, let's divide by minus 5 in the second row, so you get 0 1 and 2, and divide by 2 in the third row, then 0 1 and 2. Okay, I can see that this matrix is, again we want to make this entry 0. Okay, so we'll subtract the last two rows. So 1 3 3, 1 1, no, this is 0 2, and this will, all three entries will become 0. Okay, now you can see that if these two matrices are equal, if you solve this system of equation for the unknown C1 C2 C3, okay, so we have this vector C1 C2 C3 equal to 0 0 0. Okay, then you can see that there is a free variable, right? Because the rank of this matrix is 2. Okay, because there are only two pivot, two non-zero entry on the diagonal, so rank of this matrix is 2, but there are 3 unknowns. That means the system of equation have a infinitely many solutions. There is a free variable. Okay, because there is a free variable, you can say that this will lead to a free variable, and therefore the system has the infinitely many solutions, and hence the vectors are linearly dependent, because for independence we want a unique solution. This implies that these vectors, which are u, v and w, is linearly dependent. This collection will become linearly dependent. Okay. Therefore, the second option is correct. Okay. So whenever a system or a collection of vectors becomes linearly dependent, that means one of the vector must depend on the other two. Okay. So in this case, so that means whatever you have the span generated by u, v, and w, that will be same as span of u and v, because the w can be written as the linear combination of the first and second vector. Okay, that can be seen from the this equation only. You can see that from this equation, if you solve, you assume that this is your augmented matrix and you want to solve w as a linear combination and u comma v, then you will find that if w is c1 times u plus c2 times v, then you can see that your c2 is nothing but 2, right? And c1 plus 3 times c2 must be 3, and this will imply that c1 is 3 minus 3 times c2, it is 6, which is minus 3. That means w must be equal to 3 times v minus u. Okay, because w can be written as a linear combination of u comma v. That means the span of u comma v and the span of u v w must be same. Therefore, the correct answers are B and C. Here. Any questions regarding this problem? Okay, so if there are no other questions, let's move to the next problem. Again, the next problem is in philosophy has the same, it's the same kind of problem as the previous one. So in the previous one, we have given three vectors and we have to find if they are linearly independent or not. Here also we have given three vectors, and these vectors are alpha 1, alpha 2, and alpha 3. These are three vectors. And again, we have to find if whether they are linearly independent or linearly dependent. Okay, but we have been given some extra information. So what are that extra information? We have been given that whenever this sum is 0, whenever this linear combination becomes 0, the product of these C1 and C2 is non-zero. Okay, that means if C1 and C2 is non-zero, that means that C1 is also a non-zero value and C2 is also a non-zero value. Okay, because if one of them is 0, then the product must be 0. That means from this linear combination C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, what can we do? Because this is 0, we can write alpha 1 as a, right? What we'll do, we can write alpha 1 as minus C2 divided by C1 alpha 2 and minus C3 divided by C1 alpha 3, right? We can divide by C1 because C1 is non-zero. Okay, this shows that the alpha 1 can be written as a linear combination of alpha 2 comma alpha 3. Okay, because we can write alpha 1 as a combination of alpha 2 and alpha 3, that says that these vectors cannot be linearly independent. These vectors alpha 1, alpha 2, and alpha 3, they must be linearly dependent. And again, because alpha 1 can be written as a linear combination of alpha 2 and alpha 3, that means the span of alpha 1, alpha 2, and alpha 3 must be equal to the span of alpha 2 and alpha 3. Okay, that means B and C, these options are correct. in this case. Okay, so are there any questions? Okay, so you want to know what is a span. Okay, let me explain what is a span. Okay, so let's say we have only two vectors. Let's call them v1 and v2. We have two vectors in a vector space, okay, where this v is a vector space over R. Okay, let's say, and for simplicity, let's instead of we just write it as Rn or R2. Okay, we are taking these vectors from the R2. That means v1 must look like something a comma b, and v2 must look like something c comma d. This is one of the simplest situation. Now the span of these vectors v1 comma v2, that we define as, this is the set of all linear combination of v1 v2. That means all the possible vectors which you can get by using v1 and v2, by adding these vector or multiplying these vector by real numbers and then adding. Okay, so you can do all the linear combination like v1 plus v2, v1 minus v2, v1 plus something 3 times v2, v1 something, or let's say 5v1 times 2v2 minus. So you can take all these linear combination. Okay, so there can be lots of linear combination, infinitely many linear combination. Okay, so all the whole set of these linear combination, which we can write like this: we are taking c1 times v1 plus we are multiplying the vector v2 by c2, and we are multiplying the vector v1 by c1, and we are adding this vector. Okay, so this is an infinite set of collection of vectors where this c1 and c2, these are real numbers. Okay, so this is the span of these two vectors. Okay, so in general, how we define span? If let's say I have some n vectors in a vector space V, where again V is a vector space over, let's say, again real number R. So in general, what we do, we define a span of these vectors v1 to v comma n as the linear combination of all the vectors, as a c1 v1, c2 v2 plus. So we are adding all the vectors by multiplying some scalar up to n, where all these c1, c2, these are real numbers coming from R. So we collect all these vectors, and that collection is called a span. Okay, so is this clear to you? Okay, so if there are no questions, let's move to the next problem. Okay, so here we have to find the values of k, or for what values of k this set, this collection of these three vectors becomes a basis of R3. Okay, now we know that the R3 is a three-dimensional vector space. So what do we mean by three-dimensional vector space? That means that there are three vectors which are linearly independent. Okay, and what are those vectors? These are precisely 1 comma 0 comma 0, e2 is 0 comma 1 comma 0, e3 is 0 comma 0 comma 1. These three vectors, these are linearly independent, and if you construct the span of these vectors e1, e2 and e3, then you get the whole vector space R3. Okay, so such a collection is called a basis of the vector space, and here this e1, e2, e3 is a basis, and the number of element in a basis, it's called the dimension of the vector space. So here in this case, the dimension is 3. Okay. And whatever the base, so basis is not unique. So there can be more than one basis. Okay. But whatever the dimension of the basis is, that always remains same. Whatever basis you take, dimension will be the same. It's an invariant. Okay. So it doesn't matter which basis we take. Okay. If you take this basis, then every basis should have the same cardinality. There must be the same number of elements. Okay. So these are three vectors. Okay. So if these three vectors form a basis of R3, that means they must be linearly independent, because that is the one of the condition of a basis. Okay. So we will just check when these three vector becomes linearly independent. Okay. So what are those vectors? Let's call v1 as k, 0, 1. v2 as 1, k plus 1, 1. And then v3 as 1, 1, 1. And what do we want? We want that whenever this sum of these vectors become 0, we want that there must be a unique solution, that is c1 must be equal to 0. Okay. Now from this equation of vectors, we get a system of equation which is k, where first column is the first vector. So 1, k plus 1, 1, 1, 1, 1. So this is the, and these are our variables c1, c2, c3, and we are solving the system for the 0 vector. Okay. So let's reduce this matrix to the row echelon form. Again, our aim is to make these two entries 0, because this one is already 0. Okay. So what should we do for that? Okay, so we can multiply the last row by k. Let's multiply last row by k. This will become k, k, k. Now we can subtract the first row from the last row, so that the first entry becomes 0. This is 0, k plus 1, 1. If you subtract this from the third row, the first row, then this will become 0. This will become k minus 1, and this will also become k minus 1. Okay. Note that we cannot divide by k minus 1. Okay. That is not allowed, because we don't know if k minus 1 is a non-zero entry or not. Okay. So that is not allowed. So let's not divide by k minus 1. If you are thinking that you can divide by k minus 1, then you should not divide by k minus 1, because we don't know if it is 0 or not, because we can always divide from something which is non-zero. Okay. But then how to make this entry 0? Okay. So what we'll do, we'll just subtract one row from another one, and let's see what we get. So 1, 1, 1. Okay, just subtract from the second row the first row, or from the third row to the second row. So from k minus 1, we are subtracting k plus 1. Then this will become minus 2, and we have this here k minus 2. Okay, so what should we do next? We want to make this entry 0. Okay, let's multiply the first row by 2. Let's see what this gives. 2, 2, 2, 0, k plus 1, 1. 0 minus 2, k minus 2. Then add first and the third row. Okay, so if you add third row to the first row, then this will become 2, this will become 0, and this again becomes k, 0, k plus 1, 1, 0 minus 2, and k minus 2. Okay, let's exchange the last two rows. So this will become 2, 0, k, 0 minus 2, k minus 2, and 0, k plus 1, and k minus 2. Okay, so what do we want? We want these three vectors v1, v2, and v3 to be a basis of R3. Okay, so if these three vectors are basis of R3, that means they must be linearly independent. And for that, we want that this k plus 1 should become 0, and this k minus 2 should become non-zero. Okay, but we have not made this to be 0. Okay, let's make it 0. Okay. Okay, so what we will do, we'll multiply the second row by k plus 1 and the last row by 2. Okay, let's see what that gives. 2, 0, k. Multiply this row by k plus 1. So this is minus 2 times k plus 1. And this is k minus 2 times k minus 1. In the last row, we are multiplying by minus 2. Or we just multiply by 2. This is 2 times k plus 1. Again 2 times k minus 2. Okay. Now we add the second row to the last row, which is 2, 0, k, 0 minus 2 times k plus 1, and this is k minus 2 times k minus 1. And when you add this, this will become 0, this will again become 0, and you have 2 times k minus 2 plus k minus 2 times k minus 1. Okay, so this is the row equivalent form. Now you want that, because you want that v1, v2, v3 is a basis, you want these entries should be non-zero, because if these entries are non-zero, then only you will have a unique solution for c1, c2, c3, and that will be a zero vector. Okay, so this will just give you that k plus 1 should be non-zero, that will give k should not be equal to minus 1. And from the second one, you will have k minus 2 common, 2 plus k minus 1, that must be non-zero. That will imply k cannot be equal to 2. The value of k should not. Okay, so Dhanpal, you can unmute yourself, and you can speak whenever you want. Okay, so there will be no confusion. and interchanging of second and third row, step 1 value is wrong. Yeah, I think there is something wrong here. So where I was interchanging these rows. So I have multiplied by last row by k, and then subtract the first row, then this one k minus 1, k minus 1. Then I was subtracting from k minus 1 to k plus 1. So minus 2 and k minus 2. So up to here it is correct. Then I multiplied first row by 2. And then I added first and last row to this, also correct. Oh, so here I was wrong. So these both value cannot be k minus 2, right? Only here. So this is k minus 2, but this is 1. Okay. Then what we are doing, we are multiplying by k plus 1. Okay, so this is k plus 1 and this is k minus 2. And we are multiplying by 2 here. And then we are adding, so we get this. Okay. So this is 2 plus something. Okay, so first this we always want. Let's see what our last condition gives. We want that 2 plus k minus 2 into k plus 1 should be non-zero. Okay, so just multiply this. This has become k square minus k and minus 2. This must be non-zero. That means k times k minus 1 must be non-zero. That implies that k cannot be 0 and 1. Okay, so k cannot be 0 and 1. That is there in our last answer. And also k cannot be minus 1. Okay, so in this case, there are two options are correct. So k cannot be 0 and 1, and k cannot be 0 and minus 1. There are three values which we have to avoid. And k can take all other values, I think. Okay, so C and D answers are correct here in this case. Okay, so are there any questions? Okay, so let's move to the next problem. Here, again, it's the same kind of problem. You have been given a set, and you have to find out if the set is linearly independent or not, or if it forms the basis of this vector space P2X. Okay, so what is P2X? So P2X means we have all the polynomials of degree at most 2. Okay, this a naught, a1 and a2, they are real numbers, and they can take value 0. Okay, that means 0 polynomial is always there. So this is a vector space. So we call this a vector space of all the polynomials of degree at most 2. Okay, so why at most 2? Because the degree can be 1 also, because whenever a2 becomes 0, then degree will become 1 if a1 is non-zero. But if a1 is also 0, then it's a constant polynomial. This is our p2, and we know that this p2 has a basis which consists of 1 comma x comma x square. So this is a standard basis of p2, and the dimension of this p2x is 3 because this has a basis of element containing 3 elements. Okay. Now here we have given a set which contains how many elements? 1, 2, 3, and 4 elements. Because this set contains 4 elements, the set must be linearly dependent. Okay, this cannot be linearly independent. Okay. So the first option is incorrect, that is the linearly independent set is incorrect. And B option is correct. The set is linearly dependent. Okay, because the dimension is 3, so the maximum linearly independent element can be 3. It cannot be more than 3. Or you can check this directly. How do we check? Just put these values in a matrix, that 2 0 comma 0 1 comma 1 comma 0 3 comma 2 comma 1 and 0 comma 0 comma 1. Okay, and you can see that this is already in a row echelon form, right? This is already in a row echelon form. And if you want to solve the system of equation where this is our matrix A and this is our B, and we are solving Ax equal to B, and you can see that this system has a unique solution. And because the system has a unique solution, that is saying that the last vector x square can be written as a linear combination of other 3 vectors. Okay, you can directly see that the vector this set is linearly dependent, and so it cannot form a basis. A is also incorrect, and it's saying that no subset of S is linearly independent. Okay, this is also false. Why? Because if you take just the 3 element, the first 3, just ignore the 4th one. So ignoring 4th one means we have to take care of this matrix, the A matrix only. And this A matrix, because it is already in a row echelon form, if you want to solve this system that Ax becomes a 0 vector, that way you will have a unique solution and the x will become 0. That means the 3 vectors are linearly independent. Okay, so only option B is correct. Okay, so any doubts, any questions regarding this problem? Okay, so let's move to the next problem. Again, so 2 subspaces of R4 are given. So one subspace is S, another subspace is T, and the vectors of these subspaces are defined by this equation becoming 0. Okay, so here this one equation becomes 0, here another this equation becomes 0. And then we have to find out what is the dimension of either S, T or S intersection T. Okay, so because you can see that the 0 vector belongs to S and the 0 vector also belongs to T. Okay, so what we mean by 0 vector? This means all 4 entries are 0. That is our 0 vector. You can see that the 0 vector satisfy the conditions of this equation and conditions of this equation. That means 0 belong to S and 0 belong to T, and that will just say that 0 will be there in the intersection. Okay, that means that S intersection is a non-empty set. The intersection is a non-empty. So that means this option must be incorrect. Okay, so now let's find the dimension of S and T. Okay, so what can be the dimension of S and T? Okay, so in S, you can see that the vector satisfy this equation 2x plus y plus 3z plus w becomes 0. Okay, this means the w can be written as a linear combination of x, y, and z, right? That means you can write x as x comma y comma z. Okay, all the vectors here in S can be written as x, y, comma z, comma minus 2x minus y minus 3 times z. Okay, so these are all the vectors. So this is the subspace. So the last coordinate can be written as a linear combination of the third one. Okay, that means, okay, let's say you have this vector x, y, z, and then minus 2 times x minus y minus 3 times z. Okay, so this u vector have, and you want to write this as a linear combination. So let's see how do we write as a linear combination. Okay, so because you want first entry to be x, so let's put here 1, and here there is no contribution of x, put here 0. Again, there is no contribution of x here also, so let's put 0. There you can see a minus 2 plus y 0 1 0 minus 1 plus z times 0 0 1 and minus 3. You can see that any vector in S you can write as a linear combination of these three vectors. One is this, one is this, and one is this. Let's call it v1, v2, and v3. Okay, because any vector can be written as a linear combination of these three vectors, and now you have to just check if these these vectors are linearly independent. Okay, for checking that, just put them in a matrix and reduce that to a row echelon form. Okay, so if these vectors become linearly independent, that means the subspace has dimension 3. Okay, okay, so here okay, so only the last row is non-zero, and this is our diagonal, and below the diagonal we want everything to be 0. What you can do, just exchange first and the last row to make it into a row echelon form. Okay, now multiply the last row by 2. Let's say we have multiplied by 2, and okay, let's not do that. We can more easily make this into a row echelon form. What do? Just multiply the first row by 2 and add to the last row. Multiply the second row by minus 1, add to the last row. Multiply the third row by minus 3, add to the last row. What do you get? 1 0 0 0 1 0 0 0 1, and the whole everything will become 0. Okay, now this matrix is in a row echelon form, and there are three pivots, right? These three are non-zero entry on the diagonal, and we have three unknowns. Okay, this implies that the vectors are linearly independent, therefore dimension S must be 3. Okay, that means the first option is incorrect. Okay, what about the second subspace T? Here x plus 2y plus z plus 3w is 0. Okay, again you can see that any vector x, y, z, w, this vector we can write as x, y, z, and from here you can calculate the value of w. Okay, so what is the w? It is minus 1 by 3 x minus 2 by 3 y and minus 1 by 3 z. This is our w. Now this can be written as a linear combination of, so x times you can have 1 0 0 minus 1 by 3 you have y 0 1 0 minus 2 by 3 z times 0 0 1 and minus 1 by 3. Okay, again these three vectors have the same form as we got in the last case, in the case of S, and you can similarly you can see that these three vectors are also linearly independent, and therefore dimension of T is also 3. So dimension T is 3 again, that is all, this is one of the correct option. Now what is the dimension of the intersection? Okay, so for finding the dimension of the intersection, let's see what is the intersection. So how can we describe the intersection set? So intersection set can be described as x, y, z, w in R4, such that there are two conditions that needs to be satisfied. One from T1, that coming from T1, so x plus 2z plus the 3 times w. Okay, and one coming from the definition of S. So from S we have 2x plus y plus 3z plus w. Here we have two equations, right? Okay, so what we'll do again, we'll try to write these vectors. Okay, from the first, this second equation, this is our second equation. Let's say this is our first equation. The W is, we already know, is 2x minus y minus 3 times z. Now, what can we find from the first equation? And we can replace that. Okay, what do you do? Multiply the second equation by 3 and then subtract. So what we are doing, we are subtracting from equation 1 with 3 times 2. Okay, let's not write it like that. We are at x plus 2y plus z plus 3w. From this equation, subtract 3 times 2x plus y plus 3z plus w. This will become 0. Okay, so what this gives us, this is like x minus 6x, 2y minus 3y, z minus 9z, and the w will cancel. Okay, this we get from here. That means minus 5x minus y minus 8z becomes 0. That implies that y must be equal to minus 5x minus 8 times z. So now we can write y in terms of x comma z. We already know w as a linear combination of x, y, and z. So what was w? Minus 2x minus y minus 3 times w, right? No, minus 3 times z. Okay, now we know the value of y. So y is this, so we can put here y. It is minus 2x plus 5x plus 8z minus 3z. So this will become 3x plus 5z. Okay, so we got w also. That means any vector x, y, z, comma w is nothing but x, and here this is the value of y. That means this is 5x minus 8z and z, and the w can be written as this. So 3x plus 5z. Okay. Now this you can write as a linear combination of x comma z. So x times 1 minus 5 0 3 plus z times 0, -8, 1, and 5. Okay, you can see that there are two vectors, and you can verify that these two vectors are again linearly independent. Again, you can put them in a matrix and do the row echelon form, or you can from directly here you can see that if these two vectors are linearly dependent, that means one can be written as a linear combination or as a multiple of the another vector. Okay, but that is not the case. You cannot get one vector by multiplying the another vector by some scalar. Okay, that means these vectors are linearly independent, and therefore dimension of S intersection T is equal to 2. So dimension of S intersection T is 2. So B option is correct. So this there are two correct options. Okay, let's move to the next problem. So here there is a vector space of two dimension over R, and a map is defined between them. The map is defined in that way, and they are asking, is the map is linear? Is this map T is linear? Okay, so what do we mean by linear map? If you have a map from a vector space to itself, then we say that T is linear if there are two conditions. What are those two conditions? Whenever you add two vector, that means, so you add two vectors, then apply T, and that should be equal to the apply T first to both the vector, and then you add them. Similarly, if you multiply a vector by a scalar C and then apply T, that should equivalent to taking C outside and multiply C by the vector TV. Okay, so if these two conditions satisfy, then we say the vector it's a linear, the map is linear. Okay, so in our case, let's say two vector are arbitrary vector a comma b and b2 is c comma d. Okay, so let's verify these two conditions. So a comma b plus c comma d, we first add these vector and then apply t. What do we have? This is t of a plus c comma b plus d. So by the definition of the map, when you apply t, the first coordinate is the sum of the these first and second coordinates. So this must be a plus b plus c plus d, and this side we have a plus c minus b minus d. Okay, let's see what do we have if we do the opposite. That is, first apply tv1 and then tv2. Okay, so what is tv1? This is a plus b comma a minus b, and you are adding c plus d comma c minus d. That means this is a plus b plus c plus d comma a plus c minus b minus d. Okay, this is exactly equal to t of v1 plus v2. You can see that this equation, the first condition gets satisfied. What about the second condition? Multiply by a scalar to a vector a comma b and then apply t. That means t of ac comma bc, that must be ac plus bc comma ac minus bc. Okay, what about first applying t on AB, then multiplying by C. That means C times A plus B, comma A minus B. This will become again AC plus BC, comma AC minus BC. That means these two are also equal. That is, we have T, comma C times V1 must be same as C times T of V1. That implies that T is indeed linear. The linear map. Okay, so the assertion is correct. So B is true. Okay. Again, from R3 to R3, a linear transformation is given, a linear map is given. Okay, linear transformation is just map that we have seen before, given by two conditions. And the map is given like this. So whenever you apply T to a vector x comma y comma z, the resultant vector or the output is to make the last coordinate 0. That means we are projecting the whole three-dimensional plane, three-dimensional space to the two-dimensional plane, the xy plane. Okay, and they want that which vector generate the null space. Okay, so what is null space? Let's write null space like this. So what is the null space? The null space is all those vector x comma y comma z in R3 for which t of x comma y comma z becomes 0. That means become 0 vector. Okay. So when t of x comma y comma z becomes 0 vector, that is 0 comma 0, we just apply the definition of t, you will have x comma y comma 0. That will give you x must be 0 and y must be 0. Okay. That means the null space of t is given by 0 comma 0 comma z, where z belongs to the R. That means the whole space, this is a span of only one vector. Okay, the span of which vector? 0 comma 0 comma 1. Right, you are multiplying the last coordinate by z. Okay? So the null space is generated by the 0 comma 0 comma 1. So the option C is correct. Okay, again a linear map is here. T is a linear map, and t of 1 comma 0 is this, t of 0 comma 1 is this, and you have to find t of 2 comma 1. Okay, so we have to find t of 2 comma 1. What is this? Okay, so for that we will write 2 comma 1 as a linear combination of or these two vectors, g1 comma 0 and 0 comma 1. You can see that it can be written as twice of 1 comma 0 plus 1 times 0 comma 1, right? Now because t is linear, t of 2 comma 1 is same as twice of t of 1 comma 0 plus t of 0 comma 1. So what is t of 1 comma 0? That is given is twice of 1 comma 2 or this, and t of 0 comma 2 comma 1. Okay, so this give you 4 comma 5. This option A is correct. Again, in this problem, you have to find again a linear map is given, and you have to find what is the rank of t. Okay, so for finding the rank of t, we will use the rank nullity theorem. So what rank nullity theorem says? It says that the rank of a map T plus its nullity is must be equal to the dimension of the domain vector space. It means rank plus nullity must be 2. Okay. So for finding rank, we will just find the nullity. If we have the nullity, then we have the rank. Okay. So for finding the dimension of the null space, we want that all those vectors such that for which t of x comma y becomes 0 comma 0. That means x plus y must be 0, x minus y must be 0, and 3 times x must be 0, right? Because 3 times x is 0, that implies that x must be 0. Now from this equation, because x becomes 0, this will just imply that y becomes 0. Okay, that means there is a unique solution that x comma y must be 0 comma 0. So there is nothing inside null space except the 0 vector. That means the dimension of the null space is 0. Okay. And from the rank nullity theorem, we have rank of t is equal to 2 because the nullity of t becomes 0. Okay, so here option D is correct. Okay, so we'll just, because we are already running out of time, so we'll just end our tutorial here. Thank you very much for joining this live session, and let's meet with a new set of problems next week.